Section 14.4, titrations and pH curves. You will, I am sure, do a titration in lab. Titrations come in two types. We have either what are called stoichiometric or endpoint titrations, in which we're going to use a titrant, so it's often an acid or a base, to determine the concentration of an unknown solution. Right? Or we could have what's called a pH curve titration, which is going to give us a little bit more information about a particular acid or base. So a titration is used to determine the amount of acid or base in a solution. We can do titrations with other things. We can do electrochemical titrations. The definition of a titration is that a measured amount of a titrant of known concentration that reacts in a stoichiometrically established manner with a known volume of a solution with an unknown concentration of titrate. So this involves a solution of known concentration, the titrant, delivered from a burette or burette to the unknown solution, unknown in terms of its concentration, until the substance analyzed is just consumed. So this is what we call an endpoint. The equivalence point or stoichiometric point is the point in the titration where the stoichiometrically equivalent amounts, or the amount of base, has been added to exactly react with all the acid originally present, or vice versa. And it is the endpoint is signaled by the color change of the indicators. And note that these are two different terms. You've got endpoint and you've got equivalence point. Equivalence point is talking about stoichiometry, and endpoint is talking about color change in an indicator, and they are not the same thing. Right? We want them to ideally be very, very close to each other, but they're not the same thing. A pH curve, or a titration curve, is the plot of pH of a solution being analyzed as a function of the amount of titrant added. It helps to monitor the progress of an acid-base titration. Since titrations usually involve small quantities, oftentimes millimoles are used, where 1 millimole is going to be 1 mole divided by 1,000. The reason is that oftentimes you're not going to use liter-type volumes. You're going to use milliliter-type volumes. And so 1 millimole per milliliter has the same concentration as 1 mole per 1 liter. All you're doing is dividing the numerator by 1,000 and dividing the denominator by 1,000, and so those thousands will cancel each other out. The molarity can be defined in terms of millimoles per milliliter. So molarity is moles of solute per liter of solution, and we're going to divide each of those by 1,000 to give us millimoles per milliliter. The number of millimoles of solute can be obtained from the product of the volume in milliliters and the molarity. So we're going to do millimoles is equal to our volume in milliliters times molarity. Honestly, if this is confusing, just do it in liters. Do it in moles. Do it in molarity. If this is throwing you, right, just take all the milliliters they're going to give you and convert them from milliliters back into liters. And all these millimoles, just convert them into regular moles. Yeah, you're going to deal with an exponent, but who cares, right? You just deal with that as an exponent, and that way you're not confusing your units. I think it is much more likely that you will make a mistake confusing units than you will confusing an exponent. This is what a titration curve is going to look like. This is a pH curve for the titration of 5 milliliters of 0.2 molar sodium hydroxide with 1 molar nitric acid with 0.1 molar sodium hydroxide. So our pH is going to go up as we add in more volume. So our burette is going to hold our sodium hydroxide. I'll drip little drops in there. And we're going to put it into a flask containing our nitric acid. And as we add in, we're going to see the pH goes up as we're starting to neutralize our strong acid with our strong base. And then our pH will shoot up dramatically. At the equivalence point, we have just water and salt. So here it would be sodium nitrate. And our pH is going to be 7, right? And so this is one of the characteristics of a strong acid, strong base titration is that the pH is going to be 7. We know that we're titrating with a strong base because our pH increases up to about 13, and we're starting off with a very low pH because we started off with acid. Before the equivalence point, the H plus, and hence pH can be calculated by dividing the number of millimoles of H plus remaining by the total volume. So notice that you're running this as a volume total. That's why this thing is going to increase, right? Where if our H plus concentration is going to go down, right? It's going down for 2 reasons. One, I've neutralized, right? I've consumed some of my H plus. And the other is that as I'm going along, right, and I've added in 50 milliliters, right, I've got our moles, right? One is a moles concern, and the other is a volume concern. I've increased my volume. And my H plus concentration is going to drop because I've both consumed moles of H plus and I've increased the total volume. Even if I didn't do anything in terms of neutralizing it, my concentration would go up if I added in sodium chloride instead of sodium hydroxide because my volume is increasing. So we're going to look at the total volume of the solution in milliliters. At the equivalence point, the pH is 7. And after the equivalence point, our hydroxide ion concentration can be calculated by dividing the number of millimoles of excess hydroxide by the total volume of the solution. So then our H plus is obtained from Kw. Okay? So anywhere along here, right, we're just looking at how much strong acid do I have. Anywhere up along here, I'm just doing a how much excess hydroxide. Right? It's a strong base problem. Now I'm going to find out how many moles of hydroxide I have, divide by the total volume. Now this total volume tie will often confuse people, so make sure you're doing your initial volume plus your added volume. If we've got a titration where we're starting off with a strong base, and we're adding in, and we're going to add in a strong acid, we're going to start off at a high pH. As we add in our acid, right, our concentration of hydroxide will decrease, right? 1, because we've neutralized it, and 2, we've increased our volume, right, until we reach the equivalence point, and that's where we have just water and our salt, and that's going to be pH neutral. pH will drop drastically as we add in more strong acid. Right. Calculating the pH from a weak acid strong base titration is going to involve 2 steps. Step number 1 is going to be a stoichiometry problem. The reaction of a hydroxide ion with the weak acid is assumed to run to completion. So we're going to have our HA reacting with our hydroxide to give us the conjugate base. The concentration of the acid remaining in the conjugate base are then determined. At that point, we can set up an ice table. Or what I will show you is that step 2 is an equilibrium problem. So this is our ice table, or what I'm going to show you is that we can do a Henderson-Hasselbalch through part of that. Okay. So let's look at an example. Hydrogen cyanide gas, HCN, is a powerful respiratory inhibitor. It is highly toxic. It is a very weak acid. Our Ka is 6.2 times 10 to the minus 10 when dissolved in water. So if a 50 milliliter sample of 0.1 molar hydrogen cyanide is titrated with 1 molar sodium hydroxide, we're going to calculate the pH of the solution at 3 different points. 1, 2, 3. After you've added in 8 milliliters of your strong base, at the halfway point, and this is a very special point, and at the equivalence point of the titration. Right? Are the general shape of our titration curve is going to look something like this, where we're going to start off with a weak acid. We're going to enter what's called the buffer region. And then we're going to increase our pH sharply. We're going to hit an equivalence point that is going to be up above 7, where we just have A minus in solution, right? Our buffer region, we have a mixture of HA and A minus. And when we start off, it's just the weak acid. And then once it reaches the equivalence point, it's just going to act like a strong base. So let's take a look at what we're going to do with those. After 8 milliliters of 0.1 molar sodium hydroxide have been added, the following calculations are going to apply. So before, we had 50 milliliters times 0.1 molar, or 50 millimoles of HCN. Our hydroxide, we're having 8 milliliters of 0.1 molar, so we're going to add in 0.8 millimoles. Right? We'll subtract because we're going to consume some of our weak acid to form our conjugate weak base. So we start off with nothing, and then we're going to add in 0.8 of our CN minus. Our hydroxide concentration is going to go to 0 because we neutralized all of it. And then our HCN concentration is going to decrease by 0.8. Okay. So since the solution contains hydrogen cyanide, and sodium and water, the position of the acid dissociation equilibrium is going to determine the pH. So we're going to do our HCN is going to give us H plus and CN minus. But now we're looking at what this newer amount of HCN is. So we're taking 0.42 millimoles and we're going to figure out the volume total to find our concentration. And we're going to do the same thing for our conjugate base. So we're going to do 0.8 moles divided by the volume, the total volume. Right? And our H plus concentration initially is going to be 0. We'll lose a little bit of our conjugate acid to form a little bit of our conjugate base and some hydronium, H plus. Throw that into our ice table. We've got our initial values. We've got our change. And then we've got our equilibrium values. And notice that this V total down here is the same for both of them. V total should be the same on all of the things, right? Because you're not going to do half in one beaker and half in another beaker. Substituting the equilibrium concentrations, and we're going to have our numerical value for K is going to be products over reactants. We're just going to do X and then 0.8 over 58 and 4.2 over 58. And these X's are going to be small, right? So we're going to get rid of these guys. We're going to end up solving for X, 3.3 times 10 to the minus 8 molar, which is our H plus concentration, and our corresponding pH is going to be 8.49. At the halfway point of the titration, the amount of HCN originally present can be determined by the original volume and the molarity. So we're going to take our volume times our concentration to give us moles, in this case millimoles. Thus, at halfway point will occur when 0.25 millimoles of OH minus has been added. The volume of sodium hydroxide in milliliters times the concentration is going to give us 2.5 millimoles of hydroxide, or the volume that we're going to need is going to be 25 milliliters. The halfway point, our concentration of hydrogen cyanide is going to be equal to that of CN minus, our conjugate weak base, and our pH is going to be equal to pKa. This is just the Henderson-Hasselbalch equation where we get the log of 1, which is 0, so our pH is going to be equal to pKa at our half equivalence point. So our pH will be pKa, which is minus log of 6.2, and we're going to get a pH of 9.21. The equivalence point will occur when a total of 5 millimoles of hydroxide has been added. Since the sodium hydroxide solution is 1.1 molar, the equivalence point is going to occur when 50 milliliters of sodium hydroxide have been added. And if you're confused by this, like doing that math, we'll go over some of those in class. This amount is going to form 5 millimoles of CN minus. We then have an equilibrium problem where the major species in solution are going to be the CN minus, sodium, and water. So this is just going to be a weak base problem. The reaction that controls the pH involves the basic cyanide ion. So we're going to take our CN minus plus H2O is going to give us our hydrogen cyanide and some hydroxide, which is going to really control the pH. So we've got a Kb. We're going to get that by doing Kw over Ka. Kw is 1 times 10 to the minus 14. Our Ka was 6.2 times 10 to the minus 10, which means our Kb is 1.6 times 10 to the minus 5. is equal to our products over our reactants. Our initial concentration of Cn minus, we had 5 millimoles divided by a total volume of 100 milliliters. So initially we had 5 times 10 to the minus 2 molar cyanide. We had no hydrogen cyanide and no hydroxide. At equilibrium, we're going to lose a little bit of our cyanide to form a little bit of our conjugate acid, hydrogen cyanide, and a little bit of our strong base, hydroxide. We're now able to take these guys, put them into an ice table. So we'll have 0.05 minus X, and at equilibrium we'll have 0.05 minus X. Our hydrogen cyanide concentration will go up by a little bit. So will our hydroxide concentration. So we'll have X and X at equilibrium. Substituting into the equilibrium concentrations into the expression for Kb, and solving in the usual way gives us an OH minus ion concentration of 8.9 times 10 to the minus 4. And our H plus concentration, so we'll take our Kw expression, rearrange it to solve for the H plus concentration. So our H plus concentration is 1.1 times 10 to the minus 11, and our pH is 10.96. Okay. Let's do a quick concept check. Consider a solution made by mixing 0.1 moles of hydrogen cyanide with a Ka of 6.2 times 10 to the minus 10 with 0.04 moles of sodium hydroxide in 1 liter of aqueous solution. What are the majority of species immediately upon mixing? That is, before the reaction has happened. So we haven't let anything neutralize itself. All right, so before anything has happened, we have our conjugate acid, some sodium, some hydroxide, which is a strong base, and water. And what do you think is going to happen? Yeah, these things are going to react, and all of this strong base, if it's less, is going to react with all of this and leave some left over, and we're going to form some A minus. Okay? So let's calculate the pH of a solution found by mixing 0.2 moles of acetic acid with 0.03 moles of sodium hydroxide in 1 liter of aqueous solution. So this is just what we call an acid-base neutralization reaction. All right, so our pH is going to be 3.99. Let's calculate the pH of a solution made by mixing 100 milliliters of a 0.1 molar solution of acetic acid with its Ka of 1.8 times 10 to the minus 5 and 50 milliliters of 0.1 molar sodium hydroxide solution. Okay, pause, work some stuff out, should take you about 5 minutes. We should get a pH of 4.74. Let's try one more. Calculate the pH of a solution at equivalence point when 100 milliliters of 0.1 molar solution of acetic acid with a Ka value of 1.8 times 10 to the minus 5 is titrated with 1 molar sodium hydroxide solution. Our pH is going to come out as 8.72. Yep. So this is what our pH curve is going to look like for this titration. Right. We're going to start off down in the basic point, or at an acidic point. We're going to increase a little bit. It's going to be relatively flat in the buffer zone. Right. What we'll see is that halfway between the equivalence point, pH is going to be equal to pKa. Anywhere along this buffer zone, we can calculate what that is just using Henderson-Hasselbalch. We go for the easy point. At our equivalence point, we're going to be up above 7. It's going to be something acidic, something basic, sorry, because all we got left in solution is going to be our conjugate base. And then up here, it's just going to act like a strong base. The shapes, the plots between a strong acid, strong base titration, and a weak acid, weak base titration are going to be pretty stark. Right? Our strong acid is going to lay low and stay low and then really sharply increase, whereas our weak acid is going to go up a little bit and then flatten out and then gently curve and then sharp curve. Right? They're very similar after because it's really just excess hydroxide that's controlling the pH. Near the beginning of the titration of the weak acid, the pH is going to increase more rapidly than it does in the strong acid case. The titration, because down here, all we have is excess strong acid, right? And here, all along this point, we've got a buffer. The titration of a strong acid, the equivalence point occurs at 7. The titration of a weak acid, the equivalence point is greater than 7. Right? What does it look like when you've got different Ka values? They're still going to have the same curve, but they're going to change. And as you get to a stronger and stronger Ka, right? So this is the weakest, right? You're going to jump up and get flat, right? And then down here where you've got a very, very strong weak acid, it's almost going to start to look like a strong acid curve. And so the position of this buffer zone is going to change. And that's going to make sense if you think about, well, if my equivalence point here is at 50, right, my pKa is equal to pH is going to change as I change my Ka values, right? So the smaller your Ka, the higher your pKa, the more basic your buffer zone is going to be. So let's look at another example. Let's calculate a Ka. A chemist has synthesized a monoprotic weak acid and wants to determine its Ka value. To do so, you dissolve 2 millimoles of a solid acid in 100 milliliters of water and then titrate the resulting solution with 0.05 molar sodium hydroxide. After 20 milliliters of sodium hydroxide has been added, the pH is 6. What is the Ka value for the acid? Right, there's actually several ways to do this, right? So if we do a full titration curve, right, we've got 3 things we can do, right? Anywhere along here, we could do Henderson-Hasselbalch to figure out our HA to A minus ratio. At halfway to the equivalence point, right, if we can figure out what that is, our pH is equal to pKa. That's really easy. Down here where we just have our weak acid, right? We've got some number that we could measure, right? If we measured the pH here, we know what the H plus concentration is, right? And if we know what the H plus concentration is for a weak acid, that's just going to be Ka times your initial concentration. And up here, it's a little trickier to do, but at your equivalence point, where you just have A minus, if we know its pH, and if we've measured the pH on that, then we know for a weak base, our hydroxide ion concentration is going to be equal to the square root of Kb times the concentration of A minus, right? And you got to adjust for the volume. And if you know a Kb and Kw, you can find a Ka. So there's a couple of different ways that we could do this. We're going to go with what the book's doing, right? So what's the Ka value for the acid? So we're going to represent the monoprotic acid as species as Aa, and the stoichiometry is going to be as follows. So before we had 2 millimoles. We're going to add in some hydroxide. How much hydroxide? Volume times concentration. We're adding in 1 millimole. We had no A minus to start with. We don't really care about the water. After our reaction, we're only going to have 1 millimole of HA left. All of the hydroxide gets consumed, it's 0, and our A minus is going to be 0. So looking at this, I've got equal amounts of HA and A minus. Right? This to me says if I've got both of them, I could do an ice table, I could do common ion effect, or I could do Henderson-Hasselbalch. And not only could I do Henderson-Hasselbalch because these guys are equal to each other, we're at our special place. So after the reaction solution contains just HA, A minus, sodium, and water, our pH is going to be determined by that acid-base equilibrium expression for this reaction here, where weak acid is going to dissociate into H plus into A minus. Our Ka is going to be H plus times A minus over HA. We know what these two values are, right? If we measure our pH, we can figure out what H plus is. Right? So continuing on, our HA concentration is going to be our 1 millimole divided by our total volume. So we're going to get 8.3 times 10 to the minus third. And over here, we've got 8.3 times 10 to the minus third for our conjugate weak base. So our equilibrium concentrations are that we've got 8.33 times 10 to the minus third minus and plus x. And our H plus concentration is x. We're going to plug that into our ice table. We've got our A minus. We've got our X, and we've got our HA concentrations. Note that X is known here because the pH of this solution was going to be 6. So we're going to do X is equal to our H plus concentration, which is 10 to the minus pH, 1 times 10 to the minus 6. Substituting that back in, we know that our 1 times 10 to the minus 6 is going to be x. Right, so everywhere we've got that x, we're going to substitute that in. Right, and we're going to find our Ka is going to be 1 times 10 to the minus 6. Right, pH is equal to pKa. There's an easier way to think about that. The original solution contained 2 millimoles of HA. Since 20 milliliters of added 0.05 molar sodium hydroxide contains 1 millimole of OH minus, this is halfway point in the titration. So our H plus is going to be equal to our Ka, which is just saying that Henderson-Hasselbalch pH is equal to pKa, and then you could go the other way, right? So a summary of our results for this point, right? For a weak base strong acid titration, right? This is going to be for going the other way, where I've got some sort of base in here, and I've got some, like ammonia, and I've got some sort of strong acid as my titrant, like HCl. Right? So here we're going to look at converting ammonia into ammonium by adding an H plus. And we can do this with various added amounts, and we'll end up with a pH curve, and we can calculate the pH at each one of those points, right? At our equivalence point, we just have HA. Over here, after we've added in a lot of stuff, this is really just excess strong acid. Here, we're starting off with our weak, we have just A minus in solution. Right, that's just our weak base. All along here, we could Henderson-Hasselbalch it, but at 25, pH is equal to pKa, right? Note that this is going to be Ka. If they give you a Kb, convert it to a Ka and do pH equals pKa. Even if it is a base, pH is going to be equal to pKa because that Henderson-Hasselbalch does not care. You just need significant amounts of a conjugate acid and its conjugate base. All right. Using a pH monitor,